Hello and good afternoon everybody. Today we will continue with our class Mineral Chemistry and Crystallography for the GLY3632. So let us just go to this point where we stopped last time. We were talking about the solid solution mechanism. Have we done this? Yes, we have done this. We have discussed the substitutional solid solution, the substitutional solid solution in amphibole, the interstitial solid solution. We were talking about the omission solid solution. And we have discussed the exsolution. Yes, we discussed this here, and we have talked about the element diffusion and all this stuff. Yes, we have done this. So, and therefore we are now done with our solid solution mechanism in this class. So now today we will continue with the graphical representation. So with the graphical representation, I mean we are using a binary system and we are using ternary system. Here we have an example of a ternary system. That means we are having three components, and in this example we have copper, we have iron, and we have sulfur. And then we can plot in this triangle all minerals which contain copper, sulfur and irons, yeah? So, and that is now a ternary diagram in the system, copper, iron, sulfur, yeah? So that is one example. Now we are going to the first bottom here, the chemical bar graphs. So a chemical bar graph, that is then a binary system, yeah, and here the binary system contains of Al2O3 and SiO2. Here on this side we have 100% Al2O3. Here on this side we have 100% SiO2. Now we are forming a mineral which contains Al2O3 and which contains SiO2 as well. And therefore we have our polymorph minerals, the alumosilicates. We have discussed and talked about in this class also about polymorphism. So and we have then the polymorph alumosilicates. The high pressure modification is the kyanite, the high temperature modification is the silimanite, and low pressure and low temperature modification is the andalusite. Just going here to the text on the right hand, kyanite Al2SiO5 consists of, in weight percent, 63.2% aluminium oxide and 36 weight percent of SiO2. This gives in total 100%, and this is plotted directly on the line here on the top bar. Yeah, here we have the ratio. We have here the 63.2% aluminium oxide, and here from here to here the 36.8 weight percent SiO2 inside, yeah? It can also be written as Al2O3 multiplied by SiO2, which means that it consists of one molecule Al2O3 and one of SiO2. So, and this is plotted here, yeah. Here we have the whole ratio in weight percent here. So, and below we have the same molecular, and then we have 50-50. We have 50% or molecules of Al2O3 and 50% of SiO2. Did you get this? Yeah, here we have weight percent, here we have the molecules, yeah? So, and that is now for this example of kyanite, Al2SiO5 alumosilicate. Now we have here some other minerals. We have here sodium chloride, iron sulfide, calcium carbonate, and SiO2. So, and here we have now sodium chloride in atomic weight percent. So we have here, we have one atom of sodium and one atom or ion of chloride. In total we have 2 atoms or ions per formula, which leads to have 1 sodium and 1 chloride in a balanced relationship of 50%, yeah? That is 50-50. Here we have then for example 50% sodium, and here we have 50% chloride, so it's half and half, and then we having 1 sodium and 1 chloride. But if we are putting it on the axis ranging between 0 and 100%, then it's just plotting here in the middle, yeah, 50-50. So now we are going now to iron sulfate, the pyrite, yeah. So we have 2 atoms or ions of sulfur here, and we have 1 atom of iron here. So, and then we have in total 3 atoms or ions per formula, which leads to 2/3 or 67% concentration of 60% of sulfur and 33% of iron. So, and then we have here the 67% of sulfur, and from here to here we have the 33% of iron, yeah. So then we are going here to calcium carbonate, and calcium carbonate, it is the calcite or the aragonite, and here we have the ratio. Calcium carbonate can be rewritten as calcium oxide and CO2, in which there is 1 molecule of calcium oxide and 1 molecule of CO2. This means 2 molecules per formula. In other words, 1 calcium oxide and 1 CO2, and then we have again the relationship 50-50, and then it plots here in the middle of the line of our chemical bar graph. Here we have 50% CO2 in this direction, and here we have 50% calcium oxide in that direction, yeah? So now we are going to SiO2 in weight percent. So, and the SiO2, you know this by now, this is the mineral quartz. So, and when one desires a weight percent plot, one uses the data directly from the chemical analysis. A chemical analysis of SiO2 shields 46.7 weight percent in Si and 53.3 weight percent in oxygen. So, and here we have then the ratio, yeah, that is now just using weight percent. The first 2 were atomic. Sodium chloride was atomic, iron sulfate was atomic, and the calcium carbonate was molecular. So here we have the presentation or the thing in weight. So, and then we have 53.3 weight percent oxygen and 46.7 weight percent in silica, and we are plotting here. I think that should be clear, yeah? Now we are going back to our previous thing. and we started with this triangle, and here we have the bottom. We are pressing now the bottom on triangular diagrams, yeah. So, and here we have a triangle diagram. Here in every corner we have a component, and in every corner there we have 100% of such a component. So, and here for example we have a component A, here we have maybe B, here we have C. Then here we have 100% of A, here we have 90% of A, here we have 80% of A, 70, 60, and here we have 50% of A, and on this line we have 0% of A. Let us assume here we have B, then we have here 100% of B, 90% of B, here 50% of B, here 0% of component B. Here let us assume we have C, we have here 100% of C, 90% of C, 50% of C, here 10% of C, and at this line we have 0% of C. So for those minerals with more than 2 chemical components, a triangular compositional plot is commonly used. The compositions can be expressed in weight %, atomic %, or in molecular %. So now we have here 3 bottoms. So we have now the graph construction bottom. Here, as I have told you just now, we have a triangle. Here we have component A, here we have component B, here we have component C. What is written here? A triangular diagram has 3 possible chemical components at its corners. Here we have chosen 3 letters, A, B, and C, to represent 3 different components, yeah? So now we are just going here to the continue button. So we are removing the triangle, and here we have then not a ternary system. Here we are constructing then the triangle. Here we have then component 100% of A, 100% of B, 100% of C, as I just told you before, yeah? Should we do it again because it's so fancy, yeah? Yes, here we are plotting now some minerals inside. So here at this point we have 20% of the mineral A inside, and here 80% of C. Here we have, for example, 50% of B and 50% of C, whereas here we have 30% of B, that is from here to here, and 70% of A is from here to here, yeah? I think that should be clear, yeah? So, and if we have from all 3 components something inside, then your point is somewhere plotting inside the triangle, yeah? So that was now the graph construction. Any 2 component compositions, e.g. A70, B30, or B50, C50, or A20, C80, can be plotted along the respective edges. Note that the component with the higher % plots toward the 100% direction of that component. So now we are pressing the next button, that is the molecular button. So here we have now 3 oxides inside. We have here 100% magnesium oxide. Here we have 100% iron oxide. Here we have 100% calcium oxide, yeah? So, and here we have the same situation as I told you right now. Here we have 100% of magnesium oxide. Here at this edge we have 0 mole% magnesium oxide. Here the same for the iron, 0 mole% of FeO on this line. Here it becomes more and more rich in iron, and here we have then 100%. Here the same for the calcium. We have here at this edge represents 0 mole% calcium oxide. We are going from this direction into that direction, and here we have 100%. The animation shows the graphical construction of the percent line that run across a triangular diagram. We begin with the FeO percent arrow, the arrow that runs from the inclined left edge to the right hand, the 100% Fe corner. We show identical constructions of the magnesium and the calcium oxide arrows. So now we are having here the bottom continue. So here we have now the 50% calcium line, that is this reddish one. Then the other has put a 30% iron oxide line and a 20% MgO line. So this is now the 50% FeO. This is here the 30%, that is the 50% calcium oxide. That is the 30% iron line, and that is the 20% MgO line. So, and then we have a mixture of all three components, and the intersection point of 50% calcium and 20% magnesium line, as well the 30% iron line plots then here. Let us plot a pyroxene composition with the following molecular percentage. We have 50% calcium oxide, we have 20% magnesium oxide, and we have 30% iron oxide. Such a composition exists. That could be, for example, the diopside. To see an example of the plotting of the composition of bornite, click the button marked bornite. Yeah, this is now a pyroxene, and that is a diopside. Yeah, no, it's a diopside, but it has more iron inside. It's a mixture between a diopside and a Hedenbergite. Now we are doing the same thing here for the mineral bornite. Yeah. So let us now plot the bornite composition. We have bornite, we have copper inside, we have iron inside, we have sulfur inside with the following percentage in atomic percents. We have 50% copper, 10% iron, 40% silica. So and now we have drawn the line. Here we have then 40% of sulfur, that is from here to here. Here we have 0% sulfur. Then we are going up and up and up here. Then we have 40%. So then the copper we have here in this corner, the copper, here we have 50% copper. We are drawing here the line. So and then we have 10% iron, that is this line. So and then we have here the intersection point, 50% copper, 10% iron, and 40% sulfur. Now we can click here again for the pyroxene, which we have just done before right now. So and now we can just draw inside now again the composition of our pyroxene. So in that, if I would be you, then I would check this very carefully, because that is a good question for the test and for the examination. Yeah. So And that was it so far to the graphical representation of the triangle diagrams. Here we have one bottom left, that is the carbonate species, so we will also check this one. We are making now a triangle for the carbonate species and calcite, carbonate species, calcite, magnesite, siderite. Triangular diagrams are not used only for the plotting of a few compositional points, they are also used to depict the compositional extent of minerals that shown solid solution. Here we have plotted calcium carbonate, magnesite and siderite at the corners of the triangle. So and now we are pressing the continue button, as we are always doing. Then we have now the occurrence of dolomite here and here ankerite, yeah, because in the dolomite we have calcium inside and we have magnesium inside in a 50-50 percentage ratio, and here the same for the ankerite. But here we are replacing the magnesium from the dolomite with iron. Two of the carbonate end members, magnesium carbonate and iron carbonate, show complete solid solution between them. In addition, we can plot in such diagram two other species of carbonates, that is the calcium magnesium carbonate and the calcium iron carbonate. They plot halfway along the inclined edges of the triangle. Continue. Now that the 5 end member carbonate compositions are plotted, we can add additional chemical information from the literature to show the full extent of solid solution among them. And that we have here. We can hear then the continue, pressing continue. This plot shows about 250 chemical points on the basis of the recorded carbonate analysis. This diagram now shows the full extent of solid solution among the carbonate species in the calcium carbonate, magnesium carbonate and iron carbonate system. So that was now everything to the graphical representation using binary systems and using ternary systems as well. So now we are using our previous button. We are using again previous, 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 and we are now finished with part 1 out of 4 belonging to crystal and mineral chemistry. So therefore we can now go again to previous, and we are going now to module number 2. Module number 2 is entitled Crystallography External Form. So and when we are through all the 4 modules, then we are done with this class, and I will upload by the end of the week the whole software on Moodle. I hope I can do this. And then you can just click around and watch it, and I will hand you then out also 2 tests belonging to these mineralogy tutorials, which you can use for answering all the questions, and then it will not be a problem for to write the examination. So now we are going to module number 2 entitled Crystallography External Form. So When we are talking about crystallography and external form, we can subdivide our class in symmetry operations, in crystal classes. We can talk about the Miller's indices, the twinning, the crystal growth, and the stereographic projection. So now we will start today with the symmetry operations. Symmetry operations. So here, after a brief introduction to the various symmetry operations that can be seen in two-dimensional patterns on the external form morphology of idealized crystal models, the major part of the graphical program that follows illustrates the evaluation of the total symmetry content of a crystal. The symmetry operation include rotation, roto-inversion, and mirrors and center of symmetry or inversion. So these are now the symmetry operations. We have rotation, we have roto-inversion, we have mirrors, and we have the center of the symmetry or the inversion. Now we are pressing our continue button. So in the first example, we are talking about rotation axis. The second example, I have some examples about the mirror planes. The third one, we will discuss about roto-inversion axis, and number 4 deals with the center of the symmetry. So now we are starting with the most easiest one, that is the rotation axis. So here we have such a windmill, yeah? You can fold it easily just using a paper. Then you can fold them. So and there I will show you now a few examples dealing with rotation axis. Here, so we can have a two-dimensional rotation axis, a three-dimensional. Then we have a combinations of rotation axis. Now we are going to a two-dimensional rotation axis. So here we have now different objects. Here we have a marijuana plant. Here we have a square, a two-fold, that is one-fold, two-fold. Here we have a three-fold symmetry. Here a four-fold symmetry. And here we have a snow crystal or ice crystal with a six-fold symmetry. So now we are just starting with the cannabis plant. We are clicking there. So and we have a one-fold rotation axis perpendicular to the motif. So that means when we are turning it, then the motif repeated one time in 360 degrees. It's a very easygoing thing, yeah? So now we are clicking here. So and now we are rotating the cannabis. So and then the cannabis is repeating itself one time in 360 degrees. That means you can turn it one time around the whole axis within 360 degrees, and then it will repeat itself. Yeah, it's totally easy. And there we are talking then about a one-fold rotation axis perpendicular to the motif. Yeah, that's all. Yeah. Now we are going back to the two-fold axis. So and then we have here the symbol of a two-fold axis. a two-fold rotation axis with perpendicular motif perpendicular to the motif. So that means the motif repeated 2 times in 360 degree. So then we are talking about a two-fold rotation axis. So let us just check it if this is true. So now we are turning it 180 degree. It's repeating itself the first time after 180. So now we are turning it again. So and then we can repeat the motif 2 times within 360 degree, and therefore we are making now this symbol inside that is a two-fold rotation axis, yeah? Two-fold rotation axis, yeah? So now we are going to previous. We are talking now about the three-fold rotation axis. So in the three-fold rotation axis perpendicular to the motif has such a triangle as a symbol. Can you see it? That is this triangle. So that means the motif repeated 3 times in 360 degree. There are also 3 mirror lines along the centers of the petals of the motif. The three-fold rotation axis lies at the intersection of these mirror lines. So now we can repeat the whole example 3 times in 360 degree. Let us just check if this is true. We are turning it now for 90, 120 degree, it repeats itself. Now we are turning it again, we are now at 240 degree, it repeats itself. And now we are turning it again 120 degree, and it repeats itself 3 times in 360 degree. And therefore we have here a three-fold axis. So and then we have here a mirror plane, we have here a mirror plane, and we have here a mirror plane. So and about these mirror planes we will discuss later when I will show you some examples dealing about mirror planes. So now we are going now to the four-fold axis. We are clicking on it. So then we have here four-fold, and that is the symbol for four-fold, that is just a square. Four-fold rotation axis perpendicular to the motif. Motif repeat 4 times in 360 degree. That must now be the case that every 90 degree it will repeat itself. Let us check if this is true. 90 degree it repeats itself. Now we are turning it again, 180 degree it repeats itself. We are turning it again, 270 degree it repeats itself. 360 degree it repeats itself, and we have here our symbol for the four-fold axis inside. So now we are going to previous. We are going now to the six-fold axis. So six-fold rotation axis perpendicular to the motif. Motif repeated 6 times in 360 degree. There are also 6 mirror lines along the center of the petals of the snowflake motif. These intersect in the local location of six-fold rotation axis. So now when we are talking about that this crystal or this snowflake will repeat itself 6 times in 360 degree. That means it must repeat itself every 60 degree. And we have here a hexagonal shape as the symbol, yeah? So then we have here a mirror axis, we have here a mirror axis, we have here a mirror axis, then we have here a mirror plane, and a mirror plane, we have 6 mirror plane. And we have also, yes, the 6-fold rotation axis. So and now we will check if we can repeat our snowflake 6 times within 360 degree. We are turning it 60 degree, it repeats itself. We are turning it another 60 degree, it repeats itself. Turning it another 60 degree, it repeats itself, and now we have 180 degree. Now we are going to 240 degree, it repeats itself. To 300 degree, it repeats itself. And finally now 360 degree, and our snowflake crystal has repeated itself 6 times in 360 degree. And here we have the symbol of the 6-fold axis. So we have now 1-fold axis, we have 2-fold axis, we have 3-fold axis, we have 4-fold axis, and we have 6-fold axis. Now that was so far to the 2-dimensional rotation axis. Now we are going to the 3-dimensional rotation axis. So here we have an example for a 1-fold rotation axis, a 2-fold rotation axis, a 3-fold rotation axis, a 4-fold rotation axis, and a 6-fold rotation axis. We are selecting one of the icons on the left. So here we have now a crystal, and this crystal faces repeat now 1 time in 360 degree. Let us check if this is true. Yes, indeed, that is true. We are turning the whole crystal 1 time, and then it repeats itself in 360 degree. We can do it again and again and again, yeah? So, and you can do it then at home also again and again and again, yeah? So now we are going to the 2-fold axis. So here we have again the symbol for the 2-fold rotation axis. We have here the letter A. So and now we are checking how, if it is true that A, this letter A, has a 2-fold rotation axis. We are turning it, and 1 time in 180 degree, and the second time in 360 degree. That is typically for a 2-fold rotation axis. Now we are checking the 3-fold rotation axis with the triangle as a symbol for the 3-fold rotation axis. So in the crystal faces repeated 3 times in 360 degree. 1 time, 2nd time, 3rd time. So and then we have a 3-fold rotation axis. We are going now to the next example dealing about a 4-fold rotation axis. We have here as a symbol now again the square, and the crystal phases will repeat 4 times in 360 degrees. Let us just check if this is true. One time after 90, second time after 120, third time after 270, and the fourth time it's 360 degree, means we are repeating all the 4 phases 4 times in 360 degree, and then we are talking about the 4-fold rotation axis. So and now we are going to the 6-fold rotation axis. We have here again the symbol for a 6-fold rotation axis. So and then we are checking if this is true, if the crystal phases will repeat 6 times in 360 degree, which means every 60 degree. First time 60 degrees, second time, third time at 180, fourth time at 240, fifth time, and then finally at the 6 times in 360 degree. We are dealing then with a 6-fold rotation axis. So that was so far the differences between the 2-dimensional rotation axis and the 3-dimensional rotation axis. So now we are coming to a combination of rotation axes. So we have now a few examples. The following animations will illustrate that regular well-formed crystals may exhibit several rotation and/or roto-inversion axes at various crystallographic orientations with respect to the crystal. So here we have now the perspective view. We have here a square or a cube, and then we have here an axis going through, here an axis goes through, and here an axis goes through. So and now we are making our first exercise, which will show us something about axis rotation. So and then we have here a 4-fold rotation axis with this square as a symbol. Equivalent crystal phases repeat 4 times in 360 degree. All 3 crystallographic axes will have the same symmetry. Let us just check if this is true. Yes, here after 90 degree, 180, 270 and 360 degree. So this was now the 4-fold rotation axis. So then we have the edge diagonal rotation. So here we have again now our cube crystal, but with a 2-fold rotation axis. So because we are dealing now with edge rotation. So if we are dealing with a 2-fold rotation axis like here, then we have equivalent crystal phases repeat 2 times in 360 degree. All 6 equivalent edge diagonals have the same symmetry. So we have here 1 time, 2 times. There we have then a combination between a 4-fold rotation axis on this cube and then additionally a 2-fold rotation axis when we are talking about edge diagonal rotation, yeah? And now we are adding the roto inversion. So now we are just having here a 3-fold roto inversion axis, 3-fold with the triangle, 3 over sign here with this barrow. So because we are now going from these small crystal faces through the crystal into this one. So each crystal face has an equivalent generated by 120-degree rotation with inversion. All 4 equivalent body diagonals have the same symmetry. So now we are just putting our axis here through, and we will now check it. Here we have now a 3-fold roto inversion axis. At first 120 degree, can you see it in blue? Then we are making the inversion, then we are making a rotation, and then we are making the inversion. And then the 120-degree rotation, the inversion, and the rotation at 120 degree. So we have now, when we are looking at this cube, we have a 4-fold rotation, we have a 2-fold rotation, and we have a 3-fold roto inversion axis. So, and that is the way how we are describing crystals. So there we have now discussed the 2-dimensional rotation axis, the 3-dimensional rotation axis, and the combination of the rotation axis. So that was now the first point from our symmetry operations. Now we are coming to our next subject, dealing with the mirror planes. So we can have 2-dimensional mirror planes, and we can have 3-dimensional mirror planes. So here in this long set we have a mirror, and then we have here the original motif, and that is just the hand. And then on the other side from our mirror we have then the reflected motif. So, and then we can see our hand just reflected on the other side of the mirror, yes? So, and these are mirror planes, yeah? So, and mirror planes are also a very important symmetry element when we are talking about crystallography, yeah? So we have then 2-dimensional mirror planes. Here we have again our cannabis. So we have now here the mirror plane. It's just going from the bottom to the top. We are repeating it. Here we have one half of the side, and now we are having here the mirror plane, and we are getting exactly the same motif on the other side. That means we have here one mirror plane. So in this motif, the left hand side is mirrored into the identical right hand side. So then we have here two mirror planes. Here we have one mirror plane. Here we have an example for a two mirror plane. We are making the first one mirroring from here to there, and then the second mirror plane we have here. So we have here a mirror plane, and we have here a mirror plane. So this pattern shows the presence of two mirrors or mirror lines at 90 degrees to each other. At the point of the intersection of the two mirrors or mirror lines, a two-fold rotation axis occurs perpendicular to the screen. We are pressing now the repeat button. We have here one mirror plane, and then we have here another mirror plane or mirror lines, yeah, and then you have here the symmetry for the two-fold rotation axis in the middle together with the two mirror planes, yeah. And then we have here a four mirror planes, a motif with four mirror planes, yeah. Then we have here the first one, the second one, the third one, and the fourth one. This pattern shows the presence of two independent sets of mirror lines at 45 degrees to each other. These intersect in a four-fold rotation axis, and here we have the sign for the four-fold rotation axis here, perpendicular to the screen. We can just repeat the whole thing. First one, second one, third one, fourth one, and the symbol for the four-fold rotation axis in the middle, yeah? So there we had now some examples of two-dimensional mirror lines. So now we are going to the three-dimensional mirror planes, yeah, and here we have some examples. Here we have in crystal, we are having one mirror plane. Here we have one showing two mirror planes, and here one with having three mirror planes. We are starting with this one having one mirror plane. So, and the red line shows the position of the mirror planes, yeah? So we are pressing here. So here we have now the position of the mirror planes, yeah, here. Should we do it again? Here we have the mirror plane. Here we have it again. And the sign for the mirror plane is a M for mirror, yeah? So now we have here two mirror planes. We have here a mirror plane, two mirror planes parallel to the vertical axis. Red lines show the position of the mirror planes. So here we have the mirror plane, yeah? So next mirror plane, so we have two mirror planes in our crystal. So and now here, last not least, I have an example showing three mirror planes parallel to the vertical axis. Red lines show the position of mirror planes. So here we have one, here we have one, here we have one, and here we have the next one. So we have then 3 mirror planes parallel to the vertical axis. And now we have I gave you a few examples about 2-dimensional and 3-dimensional mirror planes. So now we are going to our point number 3, and there we will talk about the roto-inversion axis. So a roto-inversion axis, we have always this barrow at the top of our number. Here we have the number 3. It's a 3-fold roto-inversion axis, and here 4, it's a 4-fold roto-inversion axis. Yeah, we are clicking now on our crystal here. Yeah, we have clicked on it. So, and here we have the example about the roto-inversion axis, a 3-fold roto-inversion axis. Here with the number at 3 and the column at the top, or here with the triangle with these dots inside. So now we have here a small description. Each cube face has an equivalent face generated by 120-degree rotation and inversion. All 4 equivalent body diagonals have the same symmetry. The animation shows a cube face being rotated 120 degrees and then inverted through the center origin of the crystal. The wireframe outline of the cube face inverts through the center to an equivalent wire face outline. All necessary 120-degree rotations and subsequent inversions are shown to complete the whole cube form on this crystal. So now we are making here the roto inversion. Here we have in blue the first roto inversion. We are putting now 120-degree roto inversion from that side to this side, and that is the center of the symmetry. Then we are putting it from that side to this side. Then we have again 120-degree rotation. We are putting it to that side, and then we are making an inversion, putting it on that side. Making then again 120-degree rotation through an inversion. And afterwards 120-degree rotation. So, and that is now the 3-fold roto inversion axis. You can also train it by yourself, or you can you can just make a drawing and making then all these rotations for yourself. So now we are going to a 4-fold roto inversion. Yeah, here with the 4 and the column at the top, and here we have the sign, the square with this sign inside. So, and that is, this crystal form consists of 4 isoclast triangles. One pair of these at the top and the other rotated at 90 degrees at the bottom. The 4 faces are related by a 4-fold roto inversion axis. The animation shows a triangular face being rotated 90 degrees and then inverted through the center origin of the crystal. The 90-degree rotation and the inversion continue until this four-phased form is completed. Yes, now we have here our crystal, and now we are making here a four-fold roto-inversion axis. So just watch this movie a couple of times and following up the inversions and the rotations. So we can watch it again. We have time. So we are making now, at first we have our crystal, then we have here we are making now the first 90-degree rotation, yeah? From here to there. Then we are making an inversion from here to here. Then we are making again a 90-degree rotation from here to there, and it goes all over the symmetry, the center of the symmetry, yeah? Then we are making again an inversion and putting this face there. And then afterwards a 90-degree rotation coupled with an inversion, putting the face from here to here. So this was so far, or we had now so far some examples telling us something about the roto-inversion axis. So now we are going to the center of the symmetry. So we are subdividing between phase inversion, object inversion, and point inversion. So we will start now with the center of symmetry using the phase inversion. So crystals with a center of symmetry have a set of identical parallel phases, yeah? Here this phase is identical with the one below. This one we can find here, this one we can find there. So we have some phases which are parallel. In this animation, points on a crystal phase are inverted through the origin, and the origin is in the center. That means that is the center of the crystal to generate equivalent points on the parallel phase. Let us just do this. So here we have this phase. Here we have the crystal center, the symmetry center. So and now we are going point by point through the center of symmetry to the other side. And then we have an inverted crystal phase through the center of the symmetry on the other side. So, and here it is, yeah. We can connect all these points. Now we are getting the next parallel phase. And finally, the whole, we have shown all the parallel phases through the center of the symmetry. So now we are going to the next one, that is the, let us go to the object inversion. We have here an object, here we have the center of the symmetry, here we have the x-axis, the z-axis and the y-axis, or ABC, or 1, 0, 0, 0, 0, 1 and 0, 1, 0. So and now we can put through the center of the symmetry, we can move this object through the center of the symmetry to that side. Yeah, that means x, y, z. We have then x, y, z, and we are getting then minus x, minus y, and minus z. So, and here we have for every point x, y, z coordinates, there is an equivalent point with minus x, minus y and minus z coordinates, which is generated by inversion through the origin. So here we have a point with the coordinates x, y, z. So and now we are inverting it through the origin. So and here we have now the inverted point through the origin, that is minus x, minus y, minus z. So we are plotting the point, we have plotted the point x, y, z, we are making an inverting it through the origin, minus x, minus y, minus z. And that we have now done, and that was the inversion through the origin, the point inversion. We have a phase inversion. I have shown you an example from a phase inversion through the origin or center of symmetry, the object inversion, and the point inversion through the center of the symmetry. So that was this. That was the last thing from these 4 symmetry operation. We discussed the rotation axis, we discussed the mirror planes, we discussed the roto inversion axis, and we talked about the center of the symmetry. So, and that was now the symmetry operations, yeah. that I can also ask you in the text what do we have for different symmetry operations, yeah? So we have now discussed this bottom here dealing with the symmetry operation. Now we are going to the next bottom and talking about the crystal classes. So here we have, as usual, a small introduction into the crystal classes. The presence of symmetry operations can be evaluated in the external form, which means the morphology of a crystal, by the presence of rotation axes, roto-inversion axes, mirrors and centers of symmetry. A systematic evaluation of the presence of or absence of certain symmetry elements in natural occurring crystals leads to 32 possible symmetry elements and their combination, and they are known as the 32 crystal classes or point groups. So we have 32 crystal classes or point groups. The variable symmetry content of these crystal classes is expressed in the Harman-Margan or international notation. Also, there are 32 crystal classes. The following graphics will illustrate only 19 of them. 19 were selected out of 32 because these 19 contain a large number of mineral symmetries, or they represent classes with minerals that are of widespread geological occurrence. These 19 classes are marked in red in the following table. So this next point. The 32 crystal classes are grouped into 6 crystal systems. We have triclinic, monoclinic, orthorhombic, tetragonal, hexagonal and isometric crystal systems. Within each of these 6 systems, there is one crystal class with the highest symmetry content for that system. That crystal class is often referred to as the holoedral class. The 6 holoedral classes are among the 19 that are graphically portrayed. So now we are going to the page down bottom. The overall symmetry content of crystal classes can be grouped together in a specific crystal system, which allows for the choice of reference axes, crystallographic axes, and the appropriate angles between them. In the text introduction of each crystal system, the symbol is commonly used. This symbol implies that there is a non-equality in axial length or in certain angles. By reasons of symmetry, however, accidental equality may occur. In the graphical illustration of the symmetry content of the 19 crystal classes, the crystals are illustrated by idealized models. Visual inspections of these graphical models, analogous to the visual inspection of idealized wooden models in the laboratory, reveals their total symmetry content. Natural crystals are not used because they are commonly misshaped or distorted. The graphical illustration of each of the 19 crystal classes are related to their appropriate Harman-Margan or in international notation. A summary graphic illustrates the total symmetry content of each crystal class and also provides a photograph of similar looking natural crystal. So these are the 5 points how to handle now this chapter, and I will just press now the continue button. So what do we have here? We have here now in the first crystal class the symmetry elements, yeah? So, and then we have the crystal system, we have here the examples, we have a triclinic, a monoclinic, a orthorhombic, a tetragonal, a hexagonal, and an isometric crystal, yeah? So, and then we have in the third column the characteristic symmetry. So, for example, here we have our triclinic crystal. So, and then we have here 1 and 1 over. So that means we have a one-fold inversion or identity symmetry only, yeah? So the crystal system is triclinic and we have only a one-fold inversion or identity symmetry only. We are clicking on it. So, and then we have here first A is not B like B and is not like C. That means all the 3 axes have a different length, yeah? So, and then the angles alpha, beta and gamma are all different and they are not 90 degree, yeah? So in these system crystals are referred to 3 crystallographic axes of unequal lengths that make oblique angles with each other. Because the 2 crystal classes in this symmetry contain very little symmetry, 1 over or no symmetry. The orientation of a triclinic crystal is not straightforward. The rules to follow are: the most pronounced zone in the crystal is set vertical. The axis parallel to this zone then becomes the z-axis. That is the z-axis, yeah? A basal, number 2, a basal face is selected with the Miller index 001 that slopes forward and to the right, yeah? The 001 is usually here the z-axis. The intersection between a pronounced 1, 0, 0, it's usually A, the A face in the vertical zone, and 0, 0, 1 determines the location of the B axis. The intersection of 0, 0, 0, 1, 0 with 0, 0, 1 gives the location of the A axis. So, and now we have here the 1 over. Let us just tap it. So yes, here we have the our triclinic crystal 1 over with the symmetry 1 over. Alpha is not beta, is not gamma, is not 90 degree. Yes. And that is the A axis, the B axis and the C axis. So, and then we have here the total symmetry with photo. So that is, for example, a triclinic crystal that is in how it looks like in nature, and that is the mineral axinite, yeah? So it contains calcium, iron, manganese, aluminium, bore, silica, oxygen and the OH group, and has all forms are pinacoids. This crystal class contains the center of symmetry and we have only one inversion. Click screen to return. So now we have here the perspective view. So now we are making number C, we are making the rotation about C. So now we are equivalent crystal faces repeat one time in 360 degree. Yeah? So now we are rotating it, and after one rotation around 360 degree, everything repeats itself. Yeah, that is the one-fold rotation axis. So now we are making a phase inversion. So crystals with a center of symmetry have sets of identical parallel phases. In these animation, points on a crystal face are inverted to generate equivalent points on the parallel face, and I have shown you this before, how this look like, and now we are making again our phase inversion. Yeah, we are just going through the point of symmetry or the center of symmetry, and then we are making an inversion from this face to the other side. Now we have this, yeah? Looks beautiful, yeah? So now we are we are putting the next face on the other side, and finally we have done a phase inversion. So, and that is now for a triclinic crystal with this crystal symmetry 1 over. So then we have the crystal system, triclinic, and the characteristic symmetries is one-fold, inversion or identity symmetry only. So we have the crystal class 1 or 1 over. Now we are going to the monoclinic crystal. Here we have a monoclinic crystal. Can have the crystal classes 2, or we have M for a mirror plane, or we have 2 over M. The characteristic symmetry, we have two-fold rotation axis and or one mirror. Yeah. So we can have 2, we can have M, or we can have 2 over M. And in this example, what I will show you here now, we have a monoclinic crystal with the crystal symmetry 2 over M. Yes, that we have here. So now at first we will start here. In this system, crystals are referred to 3 axes of unequal lengths with the angles between alpha and beta. Alpha and gamma is 90 degree, but beta is bigger than 90 or larger than 90 degree. And A is not B and B is not C. So they have unequal lengths, as it is written here. So, and here if the angle beta is larger than 90 degree. Yeah? So there are 3 crystal classes in the monoclinic system. We have 2 over M, we have M and 2. So 2 stands, that is for the two-fold rotation axis perpendicular to the mirror plane, is usually taken as the B-axis. This is known as the second setting among mineralogists. The z-axis is always vertical and the a-axis is inclined downwards toward the front. Following the convention, the two-fold axis is always the b-axis. And M is always the plane containing the A and the C axis. So and now we have an example from the crystal symmetry 2 over M. So we have a 2 rotation axis and a mirror plane. So and here we have the crystal. We have here beta is not 90 degree, but alpha and gamma is 90 degree, and A is the length of A and B and C are different. So now we are going here to a total symmetry with a photo, yeah. We are getting now a monoclinic crystal with the symmetry 2 over M. So in there we have a very nice picture here that you can see, you can realize, or you can see it here very, very nice. We have here the mineral gypsum, which is a calcium sulfate with water inside, and the forms are a combination of a prism and pinacoids. Graphical summary of the total symmetry content of this crystal class. This class contains a center of symmetry not shown graphically. Here you have the rotation axis, yeah, the two-fold rotation axis that is here. And here you have the mirror plane. And the mirror plane is in the plane of C and the A axis. Yeah, as I told you before. Now we are clicking on the screen, going back. So at first we are making here now a rotation about B. Yeah, there we have our two-fold axis. So that is our two-fold rotation axis perpendicular to the mirror plane. Equivalent crystal faces repeated 2 times in 360 degrees. So that is then 1 time and 2 times. Though they have now repeated 2 times in 360 degrees. So and then we have a one-fold rotation axis. That is then a long rotation about C. Equivalent crystal phases repeat 1 time in 360 degrees. Yep, that was now 1 time in 360 degrees. So now we are going back. So and now we are coming to our next crystal class, that is the orthorhombic class. So and there we can have crystal classes 2, 2, 2. That means we have 3 times 2 rotation axes. Then we have MM2, or we have 2 over M, 2 over M, 2 over M. So we have then mirror planes, and we have 2 rotation axes. So and then we have the small explanation for the characteristic symmetry. 3 mutually perpendicular directions about which there is a binary system 2 or M. So here we have this, and now we are clicking there. So, and here we have now the orthorhombic system. The first thing what we can see, the length of A and B and C is different, but the angles between alpha, beta, gamma, or all three angles, alpha, beta, gamma, they are 90 degrees. We have here two examples. We have MM2 and 2 over M, 2 over M, and 2 over M. So crystals in this system are referred to three crystallographic axes of unequal lengths that make angles of 90 degrees with each other. In orientating an orthorhombic crystal, the longest axis is commonly chosen as the z-axis. However, orthorhombic crystals with a play habit, the z-axis turns out to be the shortest of the three axes. The crystal classes that are part of the orthorhombic system are 2 over M, 2 over M, 2 over M, MM2 and 222. The symbol in the Harman-Morgan international notation for the three crystal classes refer to the symmetry elements in order A, B, C. That is in 2 over M, 2 over M, 2 over M, and in 222 the two-fold rotation axis coincide with the locations of A, B, and C. In MM2 there is only one two-fold rotation axis coincident with the intersection of two mirrors. The two in the crystal class will be the z-axis. So now we have here two examples. We have MM2 and 2 over M, 2 over M, and 2 over M. We are starting with MM2. So at first we have here the z-axis, and here we have the b-axis, and here we have the a-axis. And at first I will show you a photo, the total symmetry with a photo. So what we have here a hemimorphite, which is a zinc silicate with OH2 and also with water inside. The forms are a combination of pinacoids and domes. Yeah? Graphical summary of the total symmetry content of this crystal class. This class lacks a center of symmetry, and here you have the two-fold axis. Can you see it? Here the two-fold axis. Click screen to return. So then we are making now a rotation about C. Here we have C. So, and that is a two-axis, yeah? MM2. We have mirror planes. One mirror plane, second mirror plane, and the two rotation axis. Rotation about C. So here we have now a two-fold rotation axis in the intersection, that is this one, yeah, and of two mirror planes. We have here a mirror plane, yeah, can you see? I mean, this side you can easily put on that side, and here you have the next one, yeah. So now we are clicking and watching our movie. Equivalent crystal phases will repeat 2 times in 360 degrees, and we have two mirrors again. We can show it again. We have time, yeah. Here that is the next mirror, here is one mirror, and we can turn it 2 times within 360 degrees. That's so far how easy this is, yeah. So now we have here an orthorhombic crystal with the crystal symmetry 2 over M, 2 over M, 2 over M. We have then an inversion, yeah? So at first we will start with the total symmetry with a photo. So, and therefore I will show you a mineral that is a barite that forms a basal pinacoid and several prisms. So the graphical summary of the total symmetry content of the crystal, of this crystal class, This class contains a center of symmetry that is inside here. Then we have here 1, 2 fold axes. Here we have another 2 fold axes, and here we have another 2 fold axes. Here we have a mirror plane, here we have a mirror plane, and here we have a mirror plane. And we have the center of the symmetry. That means that is 2 over m, 2 over m, 2 over m. Click the screen to return. So now we have here this nice axis, yeah, the 2 over m, 2 over m, 2 over m, and we rotate it about a. So that is now the a-axis. So now that the red one here is the a-axis, yeah. So we have equivalent crystal phases repeat 2 times in 360 degrees. So 2 times, yeah. So then we are making a rotation about C. So what is the C axis? That is the C here. It goes so, it goes here inside. And we have again the equivalent crystal phases repeat 2 times in 360 degrees. And we have 2 fold rotation axes perpendicular to a mirror plane, yeah. Can you see it 2 times? And we have here the mirror planes, yeah. So in the same about C. So here we have our crystal. We have again a 2 fold rotation axis perpendicular to a mirror plane. So and now we are just turning it. We can repeat our crystal phases 2 times in 360 degrees perpendicular to a mirror plane, yeah? So, and that was 2 over m, 2 over m, 2 over m. Previous. So, and again, previous. So now we are having the orthorhombic system. We are done with the orthorhombic. Now we are going to the tetragonal, that is this nice guy here. Tetragonal, we have a crystal class of 4, we have 4, or we have 4 over, or we have 4 over m. So, and then we have here as characteristic symmetry, we have 1 4-fold axis, yeah? So, and here we have even more crystal classes. We have 4 over, 4 over m, then we have 4 to 2, we have 4 mm, we have 4 over 2m, 4 over m, 2 over m, 2 over m. So we have here a lot of possibilities. So and now we will see and we will continue. I think we are getting an example of 4 over m, then the 4 over 2m, and then the 4 over m, 2 over m, 2 over m. Let us just check. So yes, these are now the example as I told you. So what is characteristic? A has the same length as B but not like C. A is A, B is A2, and the angles between alpha, beta and gamma is the same and is 90 degrees. So crystals in these systems are referred to 3 crystallographic axes that make right angles with each other. The 2 horizontal axes A are equivalent in length and interchangeable, commonly marked as A1 and A2. But the vertical axis is C is of different lengths. The length of C can be smaller or greater than the length of A1 and A2. In this system there are 7 crystal classes. 4 over m, 2 over m, 2 over m, 4 over 2m, 4m, 4 to 2, 4 over m, 4 over and 4. In the Harman-Maguire International Notation for crystal classes, in this system, the 4-fold rotation axis refers to the C axis. The second symbol in the notation, if present, refers to the axial direction of A1 and A2. The third symbol, if present, refers to the direction that are diagonal at 45 degrees to the direction of A1 and A2. So tetragonal 4 over m, we have a fourfold axis and a mirror plane, yeah, and we have a 4 over, that means we can have a symmetry operation through the center of the symmetry. So we have now here the bottom total symmetry with a photo. So, and what we do, we have here a chelate calcium wolframate, a tetragonal D-pyramid. Can you see it? Wonderful. Graphical summary of the total symmetry content of this crystal class. This class contains a center of symmetry, as I told you, here in the middle, which is not shown graphically, and here we have the fourfold axis, the symbol for the fourfold axis, and here we have a mirror plane. So, and here we are clicking the screen to return. So we are making now a rotation about C. So we have here now a fourfold rotation axis perpendicular to the mirror plane, yeah? Equivalent crystal phases repeat 4 times in 360 degrees. So now we are clicking here, and then we can watch the movie and how the crystal repeats itself 4 times within the 360 degree. So, and here you have the mirror plane, yeah? Yeah, boy. So now we are going back to our next example. We have here 4 over 2 over m. So then we have here a roto inversion, yeah? When we have this sparrow here, then we are talking about the roto inversion, yeah? Here we have the roto inversion, here we have such a crystal, and now we are going back to the total symmetry with a photo. So here we have a chalcopyrite, which is a kupfer iron sulfide with 3 tetragonal bisphenoids. So the graphical summary of the total symmetry contained of this crystal class. This class lacks a center of symmetry. Then we have here a fourfold axis, here you have a fourfold axis, and here. And here you have a mirror plane. And here you have a mirror plane, yes. And now we are checking it, how it will look like. While we are clicking the screen to return, we are making now a roto inversion. We have here a fourfold roto inversion axis, yeah, with this symbol. Each crystal phase has an equivalent phase generated by 90-degree rotation and inversion. That is the roto inversion, and now I will show it to you how it looks like in the movie. I have shown it to you before as well, yeah. We have here the 90-degree rotation. Then we have here the center of the symmetry. Through the center of the symmetry we are making the inversion, yeah. That is to this side, following by a 90-degree rotation. So, and now we are making again an inversion to that side. And finally the last inversion. So and now we are making here a rotation about A1. We have a twofold rotation axis. So now we are going to the last example where, for our tetragonal system, the 4 over m, 2 over m, 2 over m. So what means this now? You have just to check it. We have one we have one 4 rotation axis and two rotation axis, and we have mirror planes. So now we need at first a total symmetry with a photo, and we are getting now a zircon crystal. Yeah, here we have a very nice shaped zircon crystals. The forms are a combination of a vertical prism and two tetragonal dipyramids. Yeah, here you can see the tetragonal dipyramids. Graphical summary of the total symmetry contained of this crystal class. This class contains a symmetry not shown graphically. Here we have the fourfold axis, and here we have a twofold axis. Here we have a twofold axis, I mean here and here and here. So, and here we have a mirror plane, here we have a mirror plane, here we have the mirror, here we have a mirror, here we have the mirror. Yeah, we have 3 m's included, and we have the fourfold axis and twofold axis. Now we are clicking the screen for going to return. So now we are making a rotation about C. So, and then I will show you now the fourfold rotation axis perpendicular to the mirror plane. So equivalent crystal faces repeat 4 times in 360 degree. We are clicking here 1 time, 2 time, 3 time, 4 time. Yeah. So, and then we have here a mirror plane, we have here a mirror plane, and here from this side. Yeah. So that was the rotation about C. Then we are making now a rotation about A1, and we can also make a rotation about A2, but it looks like the same. So that means we have in here now the rotation about A1. A1 is this face here, yeah. There we have a twofold rotation axis perpendicular to a mirror plane, that is this one. Equivalent crystal faces repeat 2 times in 360 degree. The A2 axis has the same symmetry, yeah, because they are of the same length, and the angle between them is 90 degree, of course, then it's the same. Now we are making our twofold rotation, 1 time, 2 time, and perpendicular we have our mirror plane. So now we are going to the rotation about the edge diagonal. Yes, here we have the edge diagonal. We have here also, or here we have the edge diagonal, the green one. We have here a twofold rotation axis perpendicular to the mirror plane. Equivalent crystal faces repeat 2 times in 360 degree. The other equivalent edge diagonal has the same symmetry. Here we have our diagonal, And now we are watching the movie, and then you can see we are repeating. We can turn it 2 times, that we are repeating it 2 times in 360 degree. Going back into our next example, we are talking now about hexagonal crystal. So in the hexagonal crystal has as a characteristic symmetry at least one 6-fold axis. So here we have then the 6-fold rotation, roto inversion, the 6 axis, the 6 over m with mirror planes, 6 to 2, 6 mm, 6 rotation inversion m2, and then we have 6 over m, 2 over m, 2 over m. So then we have 3, that is trigonal, 3 roto inversion, 3 2, 3 m, 3 roto inversion, 2 over m. So these are now classes with hexagonal symmetry, and here we have as a characteristic symmetry element one 6-fold axis, and here one 3-fold axis. Now we are clicking on our hexagonal crystal and looking how it looks like. So here we have a lot of examples: 3 roto inversion, 3 2, 3 m, 3 roto inversion, 2 over m, 6 over m, 6 to 2, 6 mm, 6 over m, 2 over m, 2 over m. So we have 3 axes, A1, A2 and A3, and they are all of the same length at an intersection of 120 degrees. C is perpendicular to the plane with A1, A2, A3. So crystal belonging to this system are referred to 4 crystallographic directions instead of 3 as in the other crystal systems. The 4 axis system are after Brevet's, consisting of 3 horizontal axes of equal lengths that make 120 degree angles between their positive ends. They are referred as A1, A2 and A3. The 4th axis C is vertical. When properly orientated, one horizontal axis A2 is left to the right, and the other 2 make 120 degree angles on their side of it. In starting the index of any phase in the system, 4 numbers or letters are given, such as 1, 0, 1, roto inversion, 0, or HK 1 over L is notation is known as the Brevet-Miller symbol. The first number in the Hermann-Magar International Notation for hexagonal crystal classes refers to the C crystallographic axis. The second symbol, if present, refers to the symmetry elements parallel to A1, A2 and A3 axes. The third symbol, if present, refers to the location that are diagonally between A1, A2 and A3. So now we have here a lot of examples. We have 8 examples. We will go through all the 8 examples, of course, and we'll check all the symmetry operations for the different classes. We have here 3 over, that we are dealing here with a hexagonal crystal with a 3-fold inverse rotation axis. Well, at first we will start with the total symmetry with a photo. So, and here we have the dioptase. It is a copper silica oxide with 6 OH group, and it has a rhomboedral form. The graphical summary of the total symmetry contained of this crystal class. This class contains a center of a symmetry. Here you have the 3 times roto-inversion axis. Yeah, it is this triangle with the dot inside. Here you have A1, A3, A2. Here again the sign with the 3-fold roto-inversion axis. Click screen to return. So that means we are making now our roto-inversion. We have here the 3 over. Yeah? We are making the roto-inversion. That means here we have the sign. Here we have the symbol for the 3-fold roto-inversion axis. The small crystal face has an equivalent phase generated by 120-degree rotation and inversion until all 6 faces of this form appear. Now we are checking it if it is working. So now we have here this face. And now we are making a 120-degree rotation. Can you see it? Yes, of course. We have here the center of the symmetry. We are making here the inversion to that side, followed by a 120-degree rotation. We have it here. Now an inversion through the center of symmetry here. Now again the 120-degree rotation. Followed by the inversion through the center of symmetry. And an 120-degree inversion. So, and finally, again, we're making here the inversion through the center of the symmetry. And now we have made a 3-fold roto-inversion. And that is the hexagonal symmetry 3 over. Now we are going back to the system 3-2. So now we have here the hexagonal class 3-2. We have the z-axis, we have A1, A2, A3, and we are starting with the total symmetry, with a photo. So here, for example, we have the quartz, the low quartz, like you can find it on the Earth's surface. We have a trigonal trapezoedral forms terminating an hexagonal prism. Yeah? Graphical summary of the total symmetry contained of this crystal class. This class lacks a center of symmetry. Here we have the z-axis with the 3-fold rotation. Here we have a 2-fold rotation, 2-fold rotation, 3-fold rotation, 2, 2. Yeah? So now we are clicking back to the screen and we are making a rotation about C. So we have now a 3-fold rotation axis. That means equivalent crystal phases repeating 3 times in 360 degree. Now we can check if this is true. Yes, indeed, this is true. So and now we are going to the next symmetry element, we are making the rotation about A1. So in that we have here, and here we are facing a twofold rotation axis. Equivalent crystal faces repeat 2 times in 360 degrees. The A1 and the A3 axis have the same symmetry. So 2 times, can you see this? Wonderful, yeah? So now we are going to 3M. So we have now the hexagonal class 3M, and as usual we are starting with the total symmetry with a photo. So and therefore we have a very nice crystal that is a tourmaline containing sodium, calcium, iron, magnesium, aluminium, manganese, lithium, has also some bore inside, silica, and also an OH4 group is forms a rhomboedron, and a trigonal prism. So the graphical summary of the total symmetry content of this crystal class. This class lacks a center of symmetry. Here we have C with the symbol of a 3 times rotation axis, and here we have a mirror plane, yeah? So we are making now the rotation. We have a 3-fold axis, and we have one mirror plane, and the mirror plane is from here to here, yeah? We are making now a rotation about C. So we have here the 3-fold rotation axis. Equivalent crystal faces repeat 3 times in 360 degrees. So and that you can see here 3 times. And here is the mirror. And then when you are going here down, you have the next mirror, yeah? So now we are going back and going here to the 3 times roto inversion 2 over m. So it's also a hexagonal. We have a 3 times roto inversion and 2, and then we have mirror planes inside, and we have a 2 rotation axis inside. So we are going now again to the total symmetry with a photo. So and here we have a nice example of a rhodochrosite, that is a manganese carbonate, forming a rhomboedron. So the graphical summary of the total symmetry content of this crystal class. This class contains a center of symmetry. So here we have the 3 times roto inversion axis, and here we have 2 times rotation axis. So and here you have a mirror plane inside. We are clicking now and going back to the screen, and then we are making a rotation about A1. So we have a 2-fold rotation axis perpendicular to a mirror plane. So here we have the mirror plane, can you see it? Yes. And here we have the 2 times rotation axis. Equivalent crystal faces repeat 2 times in 360 degrees. The A1 and the A3 axis have the same symmetry. So here we are turning it now 2 times, and it will repeat 2 times in 360 degrees, and here perpendicular we have the mirror axis, yeah? So and now we are making the roto inversion. We have here now at first a photo with the total symmetry. That is also the rhodochrosite, a manganese carbonate, as I mentioned before. Here we have the same things again. We have here our 3 times roto inversion axis. So I must now not go again through in detail. Here we have the symbol for a 3-fold roto inversion axis. Each crystal face of this rhombohedron has an equivalent phase generated by 120-degree rotation and inversion. So now we are just checking it. How does this look like? So and now we have here, we are starting with the 3-fold roto inversion. We have here this plan here, yeah. So and now we are making at first our (120-degree rotation). Then we are making an inversion through the center of symmetry. Then we are making again a 120-degree rotation. Then again inversion through the symmetry, through the center of symmetry. We have it then there. Then again the 120-degree rotation, the inversion, again the 120-degree rotation, the inversion, the 120-degree rotation, the inversion, and now we have done the 3-fold rotation, roto inversion, as I told you. So now we are going back to our next symbol, 6/m. That means we have a 6-fold rotation axis and we have perpendicular mirror axis. So we have now here a very nice crystal, hexagonal 6/m. We have here A1, A2 and A3, and here we have the z-axis. And we are starting now with a total symmetry, with a photo, using a photo. And therefore we are using an apatite crystal, which forms a hexagonal prism and the pyramid, yeah. So the graphical summary of the total symmetry content of this crystal class. So you have here a hexagonal, the symmetry of a hexagonal class, and here you have the perpendicular mirror axis, yeah? That is 6/m. So now we are clicking the screen and going return. So that we have this one here, and now we are making a rotation about C. So here we have the 6-fold rotation axis perpendicular to a mirror plane, and the mirror plane is here. And here we have our 6-fold rotation axis, and here is the symbol for it. So and now we can watch the movie. So now we are repeating it 6 times in 360 degree, and indeed that's true. Now we are going to our previous slide, and going to 6 2 2, we have here a hexagonal rotation axis, and we have twofold rotation axis, that is 6 2 2. Is this true? So yes, here we have C, we have here A1, A2, A3, then we are going to the total symmetry. So the graphic symmetry of the total symmetry content of the crystal class, the class lacks a center of symmetry. There is no photo available for this totally symmetry graphic. Yeah? Here we have the 6-fold axis, and here we have a 2-fold axis, twofold, 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 twofold. I mean, that is one twofold, that is one twofold, that is one twofold. So now we are making a rotation about C. So we have here now the 6-fold rotation axis. That means equivalent crystal phases repeating 6 times in 360 degrees. Is this true? Yes, this is true. Then we are making a rotation about A1. So A1 we have then, that is the A1 is this one here, yes. And we have a twofold rotation axis, equivalent crystal phases repeating 2 times in 360 degrees. The A1 and the A3 axis have the same symmetry. We are just checking if this is true. Yes, this is true. So, and then we are making a rotation about H diagonal. So, and therefore we have then also a twofold rotation axis, therefore the crystallographic class 6 2 2. So then we have here the diagonal equivalent crystal phases repeating 2 times in 360 degrees. All 3 equivalent H diagonals have the same symmetry. Now we are checking if this is true. Yes, this is true. So we are going previous, we have now 6 2 2, now we have 6 mm. So that means we have a hexagonal system, 6, yeah, we have a 6 times rotation axis, and here we have then 2 mirror planes, yeah. You got it now, yeah. So we at first we are starting here with the total symmetry, and here we have then also again a picture from a natural crystal. So, and here we have a zinc side ZnO with it showing us a hexagonal pyramide. So the graphical summary of the total symmetry content of this crystal class. This class lacks a center of symmetry. Here we have our symbol for a hexagonal crystal. Yes, here we have then A1, A2, A3. Now we are clearing the screen and going back to our operation. So, and now here we are making now a rotation about C. We have a 6-fold rotation axis as here shown with this symbol, and we have equivalent crystal phases repeating 6 times in 360 degrees. Now we are clicking here on the movie, and we can repeat our crystal 6 times in 360 degrees. And we have 2 mirror planes. Here we have a mirror, here we have a mirror, and there. Yeah? Previous. We are going now to our last example, 6 over m, 2 over m, 2 over m. That means we have now a hexagonal crystal with a 6 times rotation axis perpendicular to a mirror plane, a 2 times rotation axis perpendicular to a mirror plane, and another 2 times rotation axis perpendicular to a mirror plane. So now we are starting again with a total symmetry with a photo. So, and here we have a beryl crystal, yeah, which forms hexagonal prism, a hexagonal dipyramid, and a basal pinacoid. So, graphical summary of the total symmetry content of this crystal class. This class contains a center of symmetry not shown graphically. Here you have the six-fold axis, and here you have the two-fold axis, and here you have a perpendicular mirror plane. Here you have perpendicular mirror plane here and there, yeah? So now we are making a rotation about C. So we have a six-fold rotation axis perpendicular to a mirror plane, equivalent crystal faces repeat 6 times in 360 degrees. 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, yes? So now we are making the rotation about A1. So we have then about A1 a two-fold rotation axis perpendicular to a mirror plane. Here is the two-fold orientation axis. Here is the perpendicular mirror plane. Equivalent crystal faces repeat 2 times in 360 degrees. The A1 and the A3 axes have the same symmetry. So now we are checking if this is true. Okay, this is true. So then we are going to the last bottom here, rotation about the body diagonal. So here we have again a two-fold rotation axis perpendicular to a mirror plane. Here is the two-fold rotation axis. Here we have our mirror plane, yeah? Equivalent crystal faces repeat 2 times in 360 degrees. All 3 equivalent body diagonals have the same symmetry. And here we have the proof. So that was so far an example for the hexagonal crystal symmetry with the crystal class 6 over m, 2 over m, 2 over m. So, and I have shown you now 8 examples, and you should go through all these examples again in detail, yeah? So now we are going to the last example, the isometric. So, and therefore we have crystal classes 2, 3, 2 over m with the 3 roto inversion axis, 4, 3, 2, 4 roto inversion 3m, 4 over m, 3 roto inversion 2 over m. So when these are isometric or cubic crystals, you have 4-fold and the characteristic symmetry of these crystal classes. You have 4 3-fold axes, each declined at 54 degrees, 44 minutes to the crystallographic axis. We having here now also examples, 1, 2, 3, 4 examples. Yes, and then we are checking now these examples, and then we are done, I think, with the 2 hours, with the 3 hours class. Yes. So here we have now A1 is AB is A3, all the axes have the same length, yeah, and all the angles between all the axes is 90 degrees. Though the crystal forms of crystals in the isometric system are referred to three axes of equal length that make right angles with each other. Because the axes are identical, they are interchangeable and all are designed by the letter A. When properly orientated, one axis A1 is horizontal and front to back. A2 is horizontal and right to left, and A3 is vertical. There are 5 crystal classes that belong to the isometric system. 4 over M with a 3 times rotation axis 2 over M. 4 times rotation axis 3M. 4, 3, 2. 2 over M with a 3 roto inversion axis and 2, 3. The Harman-Magar International Notation, the first digit refers to the 3 crystallographic axes A1, A2 and A3. If the number of 4 is 4 over, it means that there are a threefold axis. That means that there are a 3-4-fold axis of rotation or roto inversion coincident with the 3 crystallographic axes. The second number 3 over or 3 refers to the 4 diagonal direction of threefold symmetry between the corner of a cube. The third symbol of number, if present, refers to symmetry elements between the 6 parts of the opposing cube edges. If it is 2, as in 4, 3, 2, there are 6 fourfold axes perpendicular to the edges. If it is M, as in 3M, there are 6 mirror planes. Now we are going to the first example, 2, 3. So we have now at first, we are starting again with the total symmetry using a photo, yeah? So we have here a cobaltite, that is a cobalt arsenide sulfide, and it forms a tetratoid. Graphical summary of the total symmetry content of this crystal. This class lacks a center of symmetry. Here we have a threefold axis, threefold axis, threefold, threefold, and here we have twofold axis, yeah? Click to the screen to return. So we can now have a rotation about A3. That is this one, yeah, that is the A3 axis. And it has a twofold rotation. Crystal faces repeat 2 times in 360 degrees. The A1 and the A2 axes have the same symmetry. So now we are continuing here. We are turning this 3 times. And we can repeat our crystal 2 times in 360 degrees. Yeah, 2 times. Yeah, not 3 times as I just told you. Because here we are dealing with a twofold rotation axis using this symmetry. Now we are going rotation about the body diagonal, yeah? So, and here we having now a threefold rotation axis. Equivalent crystal faces repeat 3 times in 360 degrees. The other equivalent body diagonals have the same symmetry. So we can turn it 3 times in 360 degrees. That the crystal faces repeating themselves. So now we are going to 2 over M with a 3 times rotation axis. With a 3 times roto inversion. Yeah. At first we are continuing with the total symmetry with the photo. Here we have a pyrite, iron sulfide, which forms puritohedrons. Here we have the graphical summary of the total symmetry content of this crystal class. This class contains a center of symmetry. Here we have A1, A2, A3. So, and here we have the two-fold axis, and here we have the three-fold axis. And here with the dot inside, that means we are dealing here with the roto inversion axis. Yeah? So we are making now a rotation about A3, that means here. So we have here a two-fold rotation axis perpendicular to a mirror plane. Yeah, that is 2 over m, and here is the perpendicular mirror plane, and that is the two-fold rotation axis. We can turn it 2 times within 360 degrees. So now we have the 3 over, that is then the roto inversion axis, the three-fold roto inversion axis that we have here. Here you have the 3 over, that is the symbol, the triangle with the dot. Each crystal face has an equivalent face generated by 120 degree rotation and inversion. All 4 equivalent body diagonals have the same symmetry. So, and now you can just watch it here. Yeah, it's a beautiful software. Yes. So now we are making at first our 120 degree rotation, which is written there, and putting our crystal face to that side. Then we are having here again the center of the symmetry, and through the center of the symmetry we are making now an inversion and getting here the 120, getting the inversion, making again the 120 degree rotation, and then we are making again an inversion through the center of symmetry, followed by a 120 degree rotation with an inversion through the center of symmetry. So, and that is the way, always this interchanging between the rotation and the inversion, and then we can repeat our crystal faces through the center of symmetry. So now we are coming to the next example. 4 with a 4 inverse rotation axis, and then 3 times rotation with a mirror. So therefore we are starting again with the total symmetry using a photo, and here we have a sphalerite, that is a zinc sulfide, 2 tetrahedral forms, having 2 tetrahedral forms, a positive and a negative. Graphical summary of the total symmetry content of this crystal class. This class lacks the center of symmetry. Here you have the 4-fold roto inversion axis. Here you have a 3-fold, and here you have 3-fold rotation axis. Now we are making at first the roto inversion. So here we have the sign of the 4-fold roto inversion axis. Again, here the definition. Each crystal phase has an equivalent phase generated by 90-degree rotation and inversion. The A1 and the A2 axes have the same symmetry. So now we are going to this, and now we can see again how such a fourfold roto-inversion takes place. We are starting then with a 90-degree roto-inversion, of course, because we have a fourfold axis, followed by the inversion, again followed by the 90-degree rotation, and then we have again the inversion through the center of symmetry. 90-degree rotation followed by the inversion. So, and now we are going to the rotation about the body diagonal. Here we have a threefold rotation axis, yeah. Equivalent crystal phases repeat 3 times in 360 degree. All 4 equivalent body diagonals have the same symmetry. So here we have the threefold rotation axis, and here we have a mirror plane. That it is then 3M. Yeah, here is the mirror plane that is parallel 3. If you have a 3 over M, then the mirror plane would be here. So we are turning it 3 times in 360 degree. So, and now we are coming to our last example for today. 4 over M with a 3 times roto-inversion axis and 2 over M. So 4 over M, we have a 4 times rotation axis perpendicular, we have a mirror plane. Then we have a 2 times rotation axis perpendicular, we have a mirror plane, and we have a 3 times roto-inversion axis. So now we are going through all the symmetry operation, and we are starting with the total symmetry using a photo. So here we have now a fluoride crystal, that is a calcium fluoride. It's a combination of cube and dodecahedron. So we have the graphical summary of the total symmetry content of this crystal class. This class contains a center of symmetry not shown graphically. Here we have the 4 times rotation axis. Here we have 2 times rotation axis. Here we have the 3 times roto-inversion axis. Here we have a 3 times roto-inversion here and there. So, and here we have the 4-fold rotation, 4-fold rotation, and here we have 2-fold rotation, 2-fold rotation, 2-fold rotation. Here we have a mirror plane, here we have a mirror plane, here we have a mirror plane. Yep. So now we are making a rotation about A3. So then we have here the symbol of the 4-fold rotation axis perpendicular to the mirror plane. Here that is the mirror plane. Crystal phases repeat 4 times in 360 degree. The A1 and A2 axes have the same symmetry. So 90, 180, 270 and 360. Now we are making the rotation about the edge diagonal. Yeah, that is then the we have here a 2-fold rotation axis perpendicular to a mirror plane. Here we have the 2-fold rotation axis. Here we have the mirror plane. So, and now we can rotate it 2 times in 360 degrees Celsius, and perpendicular we have the mirror plane, yeah? So, and now last not least for today, we are watching the rotor inversion, the threefold rotor inversion. Each cube phase has an equivalent phase generated by 120 degree rotation and inversion. There are 4 equivalent corner diagonals in a cube. So we are starting with the 120 degree rotation, followed by an inversion through the center of symmetry. Then we are continuing with the 120 degree rotation, followed by the inversion through the center of symmetry, continuing again with the 120 degree rotation, followed by the inversion of the center of symmetry, continuing with the 120 degree rotation, followed by the inversion through the center of symmetry. Here we have now formed the bottom, and then we having last not least again 120 degree rotation, which is followed by the center of symmetry here to this phase. So and now our threefold rotor inversion is complete. Going back to previous. So now we have done the crystal classes. So, and that was now for today and for this week enough, because we have now again the 3 hours. So, and next week I will send you then, we will continue with another 3 hours. Yeah, I know there is midterm break, but then you are watching it later, or you can watch it at the same time. And I will also upload then the first test dealing with all this stuff what we have done till today. So please watch all these movies very, very carefully. Thank you very much for listening. Yeah, bye.